Let's set this timer, and when it's up, then I'll get started. Anyone who may just be showing up, we're going to take about 5 minutes. That's this timer, which I don't know how well you can see it, but that's that timer. And then we'll be starting in with structure and interpretation of computer programs. Gonna drink my water, but like the thing says, I'll be right back. Okay, that's that 5 minutes. Let's get into it. This is from MIT Press, Structure and Interpretation of Computer Programs, by Harold Abelson and Gerard J. Sussman with Julie Sussman. Next, Structure and Interpretation of Computer Programs, 2nd edition. Oops, I don't want my BRB screen to be mucking things up here. Just hide that. Structure and Interpretation of Computer Programs. Okay. This book is dedicated in respect and admiration to the spirit that lives in the computer. How's that for a way to open a book? The spirit that lives in the computer. And then a quote, I think it's extraordinarily important that we in computer science keep fun in computing. When it started out, it was an awful lot of fun. Of course, the paying customers got shafted every now and then, and after a while we began to take their complaints seriously. We began to feel as if we really were responsible for the successful, error-free, perfect use of these machines. I don't think that we are. I think we're responsible for stretching them, setting them off in new directions, and keeping fun in the house. I hope the field of computer science never loses its sense of fun. Above all, I hope we don't become missionaries. Don't feel as if you're Bible salesmen. The world has too many of those already. What you know about computing, other people will learn. Don't feel as if the key to successful computing is only in your hands. What's in your hands, I think and hope, is intelligence. The ability to see the machine as more than it was when you were first led up to it, that you can make it more. Alan J. Perlis. Contents, we have a foreword, a preface, and acknowledgements, followed by building abstractions with procedures. And I'm not going to read further into that right now. Instead, I'm going to go to the next page. Forward. Educators, generals, dietitians, psychologists, and parents program. Armies, students, and some societies are programmed. An assault on large problems employs a succession of programs, most of which spring into existence en route. These programs are rife with issues that appear to be particular to the problem at hand. To appreciate programming as an intellectual activity in its own right, you must turn to computer programming. You must read and write computer programs, many of them. It doesn't matter much what the programs are about or what applications they serve. What does matter is how well they perform and how smoothly they fit with other programs in the creation of still greater programs. The programmer must seek both perfection of part and adequacy of collection. In this book, the use of program is focused on the creation, execution, and study of programs written in a dialect of Lisp for execution on a digital computer. Using Lisp, we restrict or limit not what we may program, but only the notation for our program descriptions. Our traffic with the subject matter of this book involves us with 3 foci of phenomena: the human mind, collections of computer programs, and the computer. Every computer program is a model hatched in the mind of a real or mental process. These processes, arising from human experience and thought, are huge in number, intricate in detail, and at any time only partially understood. They are modeled to our permanent satisfaction rarely by our computer programs. Thus, even though our programs are carefully handcrafted, discrete collections of symbols, mosaics of interlocking functions, they continually evolve. We change them as our perception of the model deepens, enlarges, and generalizes until the model ultimately attains a metastable place within still another model with which we struggle. The source of the exhilaration associated with computer programming is the continual unfolding within the mind and on the computer of mechanisms expressed as programs and the explosion of perception they generate. If art interprets our dreams, the computer executes them in the guise of programs. For all its power, the computer is a harsh taskmaster. Its programs must be correct, and what we wish to say must be said accurately in every detail. As in every other symbolic activity, we become convinced of program truth through argument. Lisp itself can be assigned a semantic, another model by the way, and if a program's function can be specified, say, in the predicate calculus, the proof methods of logic can be used to make an acceptable correctness argument. Unfortunately, as programs get large and complicated, as they almost always do, the adequacy, consistency, and correctness of the specifications themselves become open to doubt, so that complete formal arguments of correctness seldom accompany large programs. Since large programs grow from small ones, it is crucial that we develop an arsenal of standard program structures of whose correctness we have become sure, we will call them idioms, and learn to combine them into larger structures using organizational techniques of proven value. These techniques are treated at length in this book, and understanding them is essential to participation in the Promethean enterprise called programming. More than anything else, the uncovering and mastery of powerful organizational techniques accelerates our ability to create large, significant programs. Conversely, since writing large programs is very taxing, we are stimulated to invent new methods of reducing the mass of function and detail to be fitted into large programs. Unlike programs, computers must obey the laws of physics. If they wish to perform rapidly, a few nanoseconds per state change, they must transmit electrons only small distances, at most 1.5 feet. The heat generated by the huge number of devices so concentrated in space has to be removed. An exquisite engineering art has been developed balancing between multiplicity of function and density of devices. In any event, hardware always operates at a level more primitive than that at which we care to program. The processes that transform our Lisp programs to machine programs are themselves abstract models which we program. Their study and creation give a great deal of insight into the organizational programs associated with programming arbitrary models. Of course, the computer itself can be so modeled. Think of it, the behavior of the smallest physical switching element is modeled by quantum mechanics described by differential equation, whose detailed behavior is captured by numerical approximations represented in computer programs executing on computers composed of, and so on. It is not merely a matter of tactical convenience to separate the identified three foci. Even though, as they say, it's all in the head, this logical separation induces an acceleration of symbolic traffic between those foci whose richness, vitality, and potential is exceeded in human experience only by the evolution of life itself. At best, relationships between the foci are metastable. The computers are never large enough or fast enough. Each breakthrough in hardware technology leads to more massive programming enterprises, new organizational principles, and an enrichment of abstract models. Every reader should ask himself periodically, toward what end? But do not ask it too often lest you pass up the fun of programming for the constipation of bittersweet philosophy. Among the programs we write, some, but never enough, perform a precise mathematical function such as sorting or finding the maximum of a sequence of numbers, determining primality, or finding the square root. We call such programs algorithms, and a great deal is known of their optimal behavior, particularly with respect to the two important parameters of execution time and data storage requirements. A programmer should acquire good algorithms and idioms. Even though some programs resist precise specifications, it is the responsibility of the programmer to estimate and always to attempt to improve their performance. Lisp is a survivor, having been in use for about a quarter of a century. Among the active programming languages, only Fortran has had a longer life. Both languages have supported the programming needs of important areas of application, Fortran for scientific and engineering computation, and Lisp for artificial intelligence. These two areas continue to be important, and their programmers are so devoted to these two languages that Lisp and Fortran may well continue into active use for at least another quarter century. Lisp changes. The scheme dialect used in this text has evolved from the original Lisp and differs from the latter in several important ways, including static scoping for variable binding and permitting functions to yield functions as values. In its semantic structure, Scheme is as closely akin to Algol 60 as to early Lisps. Algol 60, never to be an active language again, lives on in the genes of Scheme and Pascal. It would be difficult to find two languages that are the communicating coin of two more different cultures than those gathered by these two languages. Pascal is for building pyramids, imposing, breathtaking, static structures built by armies pushing heavy blocks into place. Lisp is for building organisms, imposing, breathtaking, dynamic structures built by squads fitting fluctuating myriads of simpler organisms into place. The organizing principles used are the same in both cases, except for one extraordinarily important difference. The discretionary, exportable functionality entrusted to the individual Lisp programmer is more than an order of magnitude greater than that to be found within Pascal enterprises. Lisp programs inflate themselves with functions whose utility transcends the application that produced them. The list, Lisp's native data structure, is largely responsible for such growth of utility. The simple structure and natural applicability of lists are reflected in functions that are amazingly non-idiosyncratic. In Pascal, the plethora of declarable data structures induces a specialization within functions that inhibits and penalizes casual cooperation. It is better to have 100 functions operate on one data structure than to have 10 functions operate on 10 data structures. As a result, the pyramid must stand unchanged for a millennium. The organism must evolve or perish. To illustrate this difference, compare the treatment of material and exercises within this book with that in any first course text using Pascal. Do not labor under the illusion that this is a text digestible at MIT only, peculiar to the breed found there. It is precisely what a serious book on programming Lisp must be, no matter who the student is or where it is used. Note that this is a text about programming, unlike most Lisp books, which are used as a preparation for work in artificial intelligence. After all, the critical programming concerns of software engineering and artificial intelligence tend to coalesce as the systems under investigation become larger. This explains why there is such growing interest in Lisp outside of artificial intelligence. As one would expect from its goals, artificial intelligence research generates many significant programming problems. In other programming cultures, this spate of problems spawns new languages. Indeed, in any very large programming task, a useful organizing principle is to control and isolate traffic within task modules via the invention of language. These languages tend to become less primitive as one approaches the boundaries of the system where we humans interact most often. As a result, such systems contain complex language processing functions replicated many times. Lisp has such a simple syntax and semantics that parsing can be treated as an elementary task. Thus, parsing technology plays almost no role in Lisp programs, and the construction of language processors is rarely an impediment to the rate of growth and change of large Lisp systems. Finally, it is this very simplicity of syntax and semantics that is responsible for the burden and freedom borne by all Lisp programmers. No Lisp program of any size beyond a few lines can be written without being saturated with discretionary functions. Invent and fit, have fits, and reinvent. We toast the Lisp programmer who pens his thoughts within the nests of parentheses. Alan J. Perlis, New Haven, Connecticut. Next page. Preface to the second edition. Is it possible that software is not like anything else, that it is meant to be discarded, that the whole point is to always see it as a soap bubble? Alan J. Perlis. The material in this book has been the basis of MIT's entry-level computer science subject since 1980. We had been teaching this material for 4 years when the first edition was published, and 12 more years have elapsed until the appearance of this second edition. We are pleased that our work has been widely adopted and incorporated into other texts. We have seen our students take the ideas and programs in this book and build them in as the core of new computer systems and languages. In literal realization of an ancient Talmudic pun, our students have become our builders. We are lucky to have such capable students and such accomplished builders. In preparing this edition, we have incorporated hundreds of clarifications suggested by our own teaching experience and the comments of colleagues at MIT and elsewhere. We have redesigned most of the major programming systems in the book, including the generic arithmetic system, the interpreters, the register machine simulator, and the compiler, and we have rewritten all the program examples to ensure that any scheme implementation conforming to the IEEE scheme standard, IEEE 1990, will be able to run the code. This edition emphasizes several new themes. The most important of these is the central role played by different approaches to dealing with time in computational models. Objects with state, concurrent programming, functional programming, lazy evaluation, and non-deterministic programming. We have included new sections on concurrency and non-determinism, and we have tried to integrate this theme throughout the book. The first edition of the book closely followed the syllabus of our MIT one-semester subject. With all the new material in the second edition, it will not be possible to cover everything in a single semester, so the instructor will have to pick and choose. In our own teaching, we sometimes skip the section on logic programming, section 4.4. We have students use the registry machine simulator but do not cover its implementation, section 5.2. And we give only a cursory overview of the compiler, section 5.5. Even so, this is still an intense course. Some instructors may wish to cover only the first 3 or 4 chapters, leaving the other material for subsequent courses. The worldwide website mitpress.mit.edu/sicp provides support for users of this book. This includes programs from the book, sample programming assignments, supplementary articles, and downloadable implementations of the scheme dialect of Lisp. Preface to the first edition. A computer is like a violin. You can imagine a novice trying first a phonograph and then a violin. The latter, he says, sounds terrible. That is the argument we have heard from our humanists and most of our computer scientists. Computer programs are good, they say, for particular purposes, but they aren't flexible. Neither is a violin, or a typewriter, until you learn how to use it. Marvin Minsky, Why Programming is a Good Medium for Expressing Poorly Understood and Sloppily Formulated Ideas. The structure and interpretation of computer programs is the entry-level subject in computer science at the Massachusetts Institute of Technology. I'm going to put my timer on to remind me to take a break eventually, because this is some heavy reading. At the Massachusetts Institute of Technology, it is required for all students at MIT who major in electrical engineering or in computer science, as 1/4 of the Common Core curriculum, which also includes 2 subjects on circuits and linear systems and a subject on the design of digital systems. We have been involved in the development of this subject since 1978, and we have taught this material in its present form since the fall of 1980 to between 600 and 700 students each year. Most of these students have had little or no prior formal training in computation, although many have played with computers a bit, and a few have had extensive programming or hardware design experience. Our design of this introductory computer science subject reflects 2 major concerns. First, we want to establish the idea that a computer language is not just a way of getting a computer to perform operations, but rather that it is a novel formal medium for expressing ideas about methodology. Thus, programs must be written for people to read, and only incidentally for machines to execute. I have to say, that one feels like an overstatement to me. I'd say it's important both that they be written for people to understand and for computers to execute, machines to execute. Second, we believe that the essential material to be addressed by a subject at this level is not the syntax of a particular programming language constructs, nor clever algorithms for computing particular functions efficiently, nor even the mathematical analysis of algorithms and the foundations of computing, but rather the techniques used to control the intellectual complexity of large software systems. Our goal is that students who complete this subject should have a good feel for the elements of style and aesthetics of programming. They should have command of the major techniques for controlling complexity in a large system. They should be capable of reading a 50-page long program if it is written in an exemplary style. They should know what not to read and what they need not understand at any moment. They should feel secure about modifying a program, retaining the spirit and style of the original author. These skills are by no means unique to computer programming. The techniques we teach and draw upon are common to all engineering design. We control complexity by building abstractions that hide details where appropriate. We control complexity by establishing conventional interfaces that enable us to construct systems by combining standard, well-understood pieces in a mix-and-match way. We control complexity by establishing new languages for describing a design, each of which emphasizes particular aspects of the design and de-emphasizes others. Underlying our approach to this subject is our conviction that computer science is not a science, and that its significance has little to do with computers. The computer revolution is a revolution in the way we think and in the way we express what we think. The essence of this change is the emergence of what might best be called procedural epistemology, the study of the structure of knowledge from an imperative point of view as opposed to a more declarative point of view taken by classical mathematical subjects. Mathematics provides a framework for dealing precisely with notions of what is. Computation provides a framework for dealing precisely with notions of how to. In teaching our material, we use a dialect of the programming language Lisp. We never formally teach the language because we don't have to. We just use it and students pick it up in a few days. This is one great advantage of Lisp-like languages. They have very few ways of forming compound expressions and almost no syntactic structure. All of the formal properties can be covered in an hour, like the rules of chess. After a short time, we forget about syntactic details of the language, because there are none, and get on with the real issues, figuring out what we want to compute, how we will decompose problems into more manageable parts, and how we will work on the parts. Another advantage of Lisp is that it supports, but does not enforce, more of the large-scale strategies for modular decomposition of programs than any other language we know. We can make procedural and data abstractions. We can use higher-order functions to capture common patterns of usage. We can model local state using assignment and data manipulation. We can link parts of a program with streams and delayed evaluation, and we can easily implement embedded languages. All of this is embedded in an interactive environment with excellent support for incremental program design, construction, testing, and debugging. We thank all the generations of Lisp wizards, starting with John McCarthy, who have fashioned a fine tool of unprecedented power and elegance. Scheme, the dialect of Lisp that we use, is an attempt to bring together the power and elegance of Lisp and Algol. From Lisp, we take the metalinguistic power that derives from the simple syntax, the uniform representation of programs as data objects, and the garbage collected heap-allocated data. From Algol, we take lexical scoping and block structure, which are gifts from the pioneers of programming language design who were on the Algol committee. We wish to cite John Reynolds and Peter Landon for their insights into the relationship of Church's lambda calculus to the structure of programming languages. We also recognize our debt to the mathematicians who scouted out this territory decades before computers appeared on the scenes. These pioneers include Alonzo Church, Barclay Russer, Stephen Kleene, and Haskell Curry. Bravely on to the next page. Acknowledgements. We would like to thank the many people who have helped us develop this book and this curriculum. Our subject is a clear intellectual descendant of 6.231, a wonderful subject on programming and linguistics and the lambda calculus taught at MIT in the late 1960s by Jack Wozencraft and Arthur Evans Jr. Am I going to read this? This is a lot of acknowledgements. I'm going to skip this one. Chapter 1. Building Abstractions with Procedures. The acts of the mind wherein it exerts its power over simple ideas are chiefly these three. 1. Combining several simple ideas into one compound one, and thus all complex ideas are made. 2. The second is bringing two ideas, whether simple or complex, together and setting them one by another so as to take a view of them at once, without uniting them into one, by which it gets all its ideas of relations. 3. The third is separating them from all other ideas that accompany them in their real existence. This is called abstraction, and thus all its general ideas are made. John Locke, An Essay Concerning Human Understanding, 1690. We are about to study the idea of a computational process. Computational processes are abstract beings that inhabit computers. As they evolve, processes manipulate other abstract things called data. The evolution of a process is directed by a pattern of rules called a program. People create programs to direct processes. In effect, we conjure the spirits of the computer with our spells. A computational process is indeed very much like a sorcerer's idea of a spirit. It cannot be seen or touched. It is not composed of matter at all. However, it is very real. It can perform intellectual work. It can answer questions. It can affect the world by dispersing money at a bank or by controlling a robot arm in a factory. The programs we use to conjure processes are like a sorcerer's spells. They are carefully composed from symbolic expressions in arcane and esoteric programming languages that prescribe the tasks we want our processes to perform. A computational process in a correctly working computer executes programs precisely and accurately. Thus, like the Sorcerer's Apprentice, novice programmers must learn to understand and to anticipate the consequences of their conjuring. Even small errors, usually called bugs or glitches, in programs can have complex and unanticipated consequences. Fortunately, learning to program is considerably less dangerous than learning sorcery because the spirits we deal with are conveniently contained in a secure way. Real-world programming, however, requires care, expertise, and wisdom. A small bug in a computer-aided design program, for example, can lead to the catastrophic collapse of an airplane or a dam or the self-destruction of an industrial robot. Master software engineers have the ability to organize programs so that they can become reasonably sure that the resulting processes will perform the tasks intended. They can visualize the behavior of their systems in advance. They know how to structure programs so that unanticipated problems do not lead to catastrophic consequences, and when problems do arise, they can debug their programs. Well-designed computational systems, like well-designed automobiles or nuclear reactors, are designed in a modular manner so that the parts can be constructed, replaced, and debugged separately. We need programming in Lisp. We need an appropriate language for describing processes, and we will use for this purpose the programming language Lisp. Just as our everyday thoughts are usually expressed in our natural language, such as English, French, or Japanese, and descriptions of quantitative phenomena are expressed with mathematical notations, our procedural thoughts will be expressed in Lisp. Lisp was invented in the late 1950s as a formalism for reasoning about the use of certain kinds of logical expressions, called recursion equations, as a model for computation. The language was conceived by John McCarthy and is based on his paper, Recursive Functions of Symbolic Expressions and Their Computation by Machine, MacArthur, 1960. Despite its inception as a mathematical formalism, Lisp is a practical programming language. A Lisp interpreter is a machine that carries out processes described in the Lisp language. The first Lisp interpreter was implemented by McCarthy with the help of colleagues and students in the Artificial Intelligence Group of MIT Research Laboratory of Electronics and in the MIT Computation Center. Lisp, whose name is an acronym for List Processing, was designed to provide symbolic manipulating capabilities for attacking programming problems such as the symbolic differentiation and integration of algebraic expressions. It included for this purpose new data objects known as atoms and lists, which most strikingly set it apart from all other languages of this period. Lisp was not the product of a concerted design effort. Instead, it evolved informally in an experimental manner in response to users' needs and to pragmatic implementation considerations. Lisp's informal evolution has continued through the years, and the community of Lisp users has traditionally resisted attempts to promulgate any official definition of the language. This evolution, together with the flexibility and elegance of the initial conception, has enabled Lisp, which is the second oldest language in widespread use today, only Fortran is older, to continually adapt to encompass the most modern ideas about program design. Thus, Lisp is by now a family of dialects, which, while sharing most of the original features, may differ from one another in significant ways. The dialect of Lisp used in this book is called Scheme. Because of its experimental character and its emphasis on symbolic manipulation, Lisp was at first very inefficient for numerical computations, at least in comparison with Fortran. Over the years, however, Lisp compilers have been developed that translate programs into machine code that can perform numerical computations reasonably efficiently. And for special applications, Lisp has been used with great effectiveness. Although Lisp has not yet overcome its old reputation as hopelessly inefficient, Lisp is now used in many applications where efficiency is not the central concern. For example, Lisp has become a language of choice for operating system shell languages and for extension languages for editors and computer-aided design systems. If Lisp is not a mainstream language, why are we using it as the framework for our discussion of programming? Because the language possesses unique features that make it an excellent medium for studying important programming constructs and data structures and for relating them to the linguistic features that support them. The most significant of these features is the fact that Lisp's description of processes, called procedures, can themselves be represented and manipulated as Lisp data. The importance of this is that there are powerful program design techniques that rely on the ability to blur the traditional distinction between passive data and active processes. As we shall discover, Lisp's flexibility in handling procedures as data makes it one of the most convenient languages in existence for exploring these techniques. The ability to represent procedures as data also makes Lisp an excellent language for writing programs that The ability to represent procedures as data also makes Lisp an excellent language for writing programs that must manipulate other programs as data, such as the interpreters and compilers that support computer languages. Above and beyond these considerations, programming in Lisp is great fun. Sandwich Topping says, "Oh, are you learning Lisp?" Yes, I am. I've found this book called Structure and Interpretation of Computer Programs. If we go to first, here's the cover. This came out, I believe, in the 1990s, but it still seems relevant, which is kind of an amazing fact. And yes, this book is written with Lisp as the central language, so I am learning Lisp. And I'm also learning how to say Lisp without tripping over my tongue, which is non-trivial. So far I've learned that Lisp stands for list processing. All right, next page. 1.1, the elements of programming. A powerful programming language is more than just a means for instructing a computer to perform a task. The language also serves as a framework within which we organize our ideas about processes. Thus, when we describe a language, we should pay particular attention to the means that language provides for combining simple ideas to form more complex ideas. Every powerful language has three mechanisms for accomplishing this. Primitive expressions, which represent the simplest entities the language is concerned with. Means of combination, by which compound elements are built from simpler ones. And means of abstraction, by which compound elements can be named and manipulated as units. Sandwich Topping says, "Very cool, I really like the ML languages." Oh, I didn't realize that ML and Lisp went together. That's interesting. So is ML a group of languages and Lisp is one within that group? Okay. In programming, we deal with two kinds of elements, procedures and data. Later we will discover that they are really not so distinct. Informally, data is stuff that we want to manipulate, and procedures are description of the rules for manipulating that data. Thus, any powerful programming language should be able to describe primitive data, and primitive procedures should have methods for combining and abstracting procedures and data. In this chapter, we will deal only with simple numerical data so that we can focus on the rules for building procedures. In later chapters, we will see that these same rules allow us to build procedures to manipulate compound data as well. 1.1.1 Expressions. One easy way to get started at programming is to examine some typical interactions with an interpreter for the scheme dialect of Lisp. Imagine that you are sitting at a computer terminal. You type an expression, and the interpreter responds by displaying the result of its evaluating that expression. One kind of primitive expression you might type is a number. More precisely, the expression that you type consists of the numerals that represent the number in base 10. If you present Lisp with a number, 486, the interpreter will respond by printing 486. Expressions representing numbers may be combined with an expression representing a primitive procedure, such as plus or star, to form a compound expression that represents the application of the procedure to those numbers. For example, but first, oh, go away, vest cues. Sandwich Topping says, somewhat the same, yeah, some might say ML is the more strongly typed version of something like Lisp. Very, very similar, though. Okay, it's time to bring the band hammer down on this want more views person. How do I do that? VSTQS. I mean, it's probably not even worth my effort to ban them because they're probably going to come back as someone else. But anyway, BESTQS. I don't want to ban the wrong person. Cool, I can make them go away. The raw power is shocking. Okay. For example, plus 137, 349. Okay, this is reminding me a lot of something called the beginning student language. There is a course called How to Code Simple Data on edX, and it uses something called beginning student language, which is a simplified version of Lisp that allows them to teach the course using a language that's specifically designed for beginning students. And this kind of thing where you have a parenthesis followed by a plus, and then 137 and 349 gives us 468. Yeah, that makes sense. Minus 1,334, 666, asterisk 599, 495, divide 1052, plus 2.710, 12.7. Expressions such as these, formed by delimiting a list of expressions within parentheses in order to denote procedural application, are called combinations. The leftmost element in the list is called the operator, and the other elements are called operands. So we have an operator of plus, an operand of 137, and an operand of 349. The value of a combination is obtained by applying the procedure specified by the operator to the arguments that are the values of the operands. The convention of placing the operator to the left of the operands is known as prefix notation, and it may be somewhat confusing at first because it departs significantly from the customary mathematical convention. Prefix notation has several advantages, however. One of them is that it can accommodate procedures that may take an arbitrary number of arguments, as in the following examples. Plus 21, 35, 12, 7, giving 75, and times 25, 4, 12, giving 1200. No ambiguity can arise because the operator is always the leftmost element and the entire combination is delimited by the parenthesis. A second advantage of prefix notation is that it extends in a straightforward way to allow combinations to be nested, that is, to have combinations whose elements are themselves combinations. So we can have plus this thing and that thing. There is no limit, in principle, to the depth of such nesting and to the overall complexity of the expressions that the Lisp interpreter can evaluate. It is we humans who get confused by still relatively simple expressions such as, yeah, this does look, paren plus paren times 3, paren plus paren times 2, 4, n paren plus 3, 5. I could go on, but the point is, Lisp, or rather the Lisp interpreter, knows what to do with this. Anyway, things such as this, which the interpreter would readily evaluate to be 57. We can help ourselves by writing such an expression in the form, oh, okay, so every time you get a closed paren, you on-indent a certain amount, and that helps you see how the different things get combined, first like this, and then like this, and meanwhile this and this combine, and then this, and then this, and then finally all of this. Okay, we can help ourselves by writing such an expression in the form of blah blah blah, following a formatting convention known as pretty printing, in which each long combination is written so that the operands are aligned vertically. Interesting. So the plus takes this and this. Meanwhile, this, I don't quite see it. But in any case, the resulting indentations display clearly the structure of the expression. Well, this is a long chapter. That's okay. Even with complex expressions, the interpreter always operates in the same basic cycle. It reads an expression from the terminal, evaluates the expression, and prints the result. This mode of operation is often expressed by saying that the interpreter runs in a read, eval, print loop. Observe in particular that it is not necessary to explicitly instruct the interpreter to print the value of the expression. 1.1.2 Naming in the environment. A critical aspect of a programming language is the means it provides for using names to refer to computational objects. We say that the name identifies a variable whose value is the object. In the scheme dialect of Lisp, we name things with define. Typing paren define size 2 causes the interpreter to associate the value 2 with the name size. Once the name size has been associated with number 2, we can refer to the value 2 by name, size 2, times 5 size gives 2. Here are further examples of the use of define. Define pi 3.14159, define radius 10, times pi paren times radius 314.159, define circumference paren times 2 pi radius, circumference 62.8318. Define is our language's simplest means of abstraction, for it allows us to use simple names to refer to the results of compound operations, such as the circumference computed above. In general, computational objects may have very complex structures, and it would be extremely inconvenient to have to remember and repeat their details each time we want to use them. Indeed, complex programs are constructed by building step-by-step computational objects of increasing complexity. The interpreter makes this step-by-step program construction particularly convenient because name-object associations can be created incrementally in successive interactions. This feature encourages the incremental development and testing of programs and is largely responsible for the fact that a Lisp program usually consists of a large number of relatively simple procedures. It should be clear that the possibility of associating values with symbols and later retrieving them means that the interpreter must maintain some sort of memory that keeps track of this name-object pairs. This memory is called the environment. More precisely, the global environment, since we will see later that a computation may involve a number of different environments. (1.1.3) Evaluating combinations. One of our goals in this chapter is to isolate issues about thinking procedurally. As a case in point, let us consider that, in evaluating combinations, the interpreter is itself following a procedure. To evaluate a combination, do the following. Evaluate the sub-expressions of the combination. Apply the procedure, that was 1. 1, evaluate the sub-expressions of the combination. And 2, apply the procedure that is the value of the leftmost sub-expression, the operator, to the arguments that are the values of the other sub-expressions, the operands. Even this simple rule illustrates some important points about processes in general. First, observe that the first step dictates that in order to accomplish the evaluation process for a combination, we must first perform the evaluation process on each element of the combination. Thus, evaluation rule is recursive in nature. That is, it includes as one of its steps the need to invoke the rule itself. Notice how succinctly the idea of recursion can be used to express what, in the case of a deeply nested combination, would otherwise be viewed as a rather complicated process. For example, evaluating times plus times 4, 6, end paren plus 3, 5, 7, end paren requires that the evaluation rule be applied to 4 different combinations. We can obtain a picture of this process by representing the combination in the form of the tree as shown in figure 1.1. Interesting. Oh, I want to be able to see both of these at once if I can. Okay. Times of here's the star 4, 6, that becomes 24. And the plus 2 with 24 becomes 26. Then we have the plus 357, which becomes 15. And finally, with the times of 26 and 15 becomes 390. Okay, figure 1.1, pretty cool. Each combination is represented by a node with branches corresponding to the operator and the operands of the combination stemming from it. The terminal nodes, that is, nodes with no branches stemming from them, represent either operators or numbers. Viewing evaluation in terms of the tree, we can imagine that the values of the operands percolate upwards, starting from the terminal nodes and then combining at higher and higher levels. In general, we shall see that recursion is a very powerful technique for dealing with hierarchical, tree-like objects. In fact, the percolate values upward form of the evaluation rule is an example of a general kind of process known as tree accumulation. Figure 1.1, tree representation showing the value of each subcombination. Next, observe that the repeated application of the first step brings us to the point where we need to evaluate not combinations, but primitive expressions such as numerals, built-in operators, or other names. We take care of the primitive cases by stipulating that the values of numerals are the numbers that they name, the values of the built-in operators are the machine instruction sequences that carry out the corresponding operations, and the values of other names are the objects associated with those names in the environment. We may regard the second rule as a special case of the third one by stipulating that symbols such as plus and star are also included in the global environment and are associated with the sequences of machine instructions that are their values. The key point to notice is the role of the environment in determining the meaning of the symbols in expressions. In an interactive language such as Lisp, it is meaningless to speak of the value of an expression such as plus x1 without specifying any information about the environment that would provide a meaning for the symbol x, or even for the symbol plus. As we shall see in Chapter 3, the general notion of the environment as providing a context in which evaluation takes place will play an important role in our understanding of program execution. Notice that the evaluation rule given above does not handle definitions. For instance, evaluating define x3 does not apply define to two arguments, one of which is the value of the symbol x and the other of which is 3, since the purpose of define is precisely to associate x with the value. That is, define x3 is not a combination. Such exceptions to the general evaluation rule are called special forms. Define is the only example of a special form that we have seen so far, but we will meet others shortly. Each special form has its own evaluation rule. The various kinds of expressions, each with its associated evaluation rule, constitute the syntax of the programming language. In comparison with most other programming languages, Lisp has a very simple syntax. That is, evaluation rule for expressions can be described by a simple general rule together with specialized rules for a small number of special forms. Compound procedures, 1.1.4. Oh, actually, that's a time for a break. Let's get to the BRB screen. Okay, that's it for the rest timer. Let's get back into Lisp. I've got my work timer. So, 1.1.4 Compound Procedures. We have identified in Lisp some of the elements that must appear in any powerful programming language. Numbers and arithmetic operations are primitive data and procedures. Nesting of combinations provides a means of combining operators. Definitions that associate names with values provide a limited means of abstraction. Now we will learn about procedure definitions, a much more powerful abstraction technique by which a compound operation can be given a name and then referred to as a unit. We begin by examining how to express the idea of squaring. We might say, to square something, multiply it by itself. This is expressed in our language as define, square x, close paren times x, close paren. We can understand this in the following way. Can't find my mouse somewhere. To square something, multiply it by itself. We have here a compound procedure which has been given the name square. The procedure represents the operation of multiplying something by itself. The thing to be multiplied is given a local name x, which plays the same role that a pronoun plays in natural language. Evaluating the definition creates this compound procedure and associates it with the name square. The general form of a procedure definition is define, name, formal parameters, and body, and The name is a symbol to be associated with the procedure definition in this environment. The formal parameters are the names used within the body of the procedure to refer to the corresponding arguments of the procedure. The body is an expression that will yield the value of the procedure application when the formal parameters are replaced by the actual arguments to which the procedure is applied. The name and the formal parameters are grouped within parentheses, just as they would be in an actual call to the procedure being defined. I was just going to say, I feel like we need an example of this, but it looks like they're giving maybe some examples here. Having defined square, we can now use it. Square 21, 441. Square plus 25, 49. Square of 3, 81. We can also use square as the building block in defining other procedures. For example, x squared plus y squared can be expressed as plus square x square y. We can easily define a procedure sum of squares that, given any two numbers as arguments, produces the sum of their squares. Define sum of squares x, y plus square x square y. Sum of squares 3, 4 equals 25. Okay, but what if we wanted to have like something that took an arbitrary number of formal parameters? Anyway, now we can use sum of squares as a building block in constructing further procedures. Defined fa, sum of squares plus a1 times a2. F of 5, 136. Well, what are they doing here? Take a and add 1. Take a and multiply it by 2. Do sum of squares with the result, and define that as f. F of 5 is 136. Okay. Compound procedures are used in exactly the same way as primitive procedures. Indeed, one could not tell by looking at the definition of sum of squares given above whether square was built into the interpreter, like plus and star, or defined as a compound procedure. That's interesting. 1.1.5, the substitution model for procedure application. To evaluate a combination whose operator names... Whoa. I just got a brain blank moment. Time to slow down on the... You know what? I'm gonna I want to play around with some of these things. Play around with some of these examples. I wonder if Dr. Racket has Lisp, and particularly Scheme. So how do I get a Lisp Scheme Interpreter? I wonder if it's in the footnotes of this. SCHEME Interpreter. Oh, could be online. But I'd rather have it offline. Type Control Enter to evaluate it. Or maybe it's Command Enter. Oh, there it goes. Is it going to remember my procedures if I save them in here? All right, let's zoom in a bit. It's pretty small. So backing up. We can do things like that plus and times 3 with, oh, and look, it even handles the indentation for us. That's nice. Did I do something wrong? Cannot call 8. I clearly did something wrong. Oh yeah, right here. $57, sure enough. Okay. Seems like things are working. Get some of this stuff under my fingers. Define size 2. Now what if I do size? What if I type size without a paren? Unknown identifier size. Maybe I have to do it like this. Well, don't tell me it can't. Oh, maybe I have to do it like this. That's how it has to go. Right, because 2 is not a procedure, it's a variable. Let's copy down this code because I think I'm gonna like get some more intuition about it if I write it down. Define pi such and such. Define radius and evaluate times pi by times radius. That's interesting. Yeah, 314 and so on. Then we define circumference as times 2 pi radius and give me circumference. 62.8318. Okay, that's cool. I wonder if this interpreter is running like locally, or if it's running in the cloud somewhere and there's a server that's interpreting it. I don't know. Okay, evaluating combinations. We saw that tree. Compound procedures. Right, define square x as times x. Compound procedure, which has been given the name square. Define, in general, it's define name formal parameters, then the body. Okay. Having defined square, we can now use it. Square 21. Yeah, 441. Let's do square of 3. $81. Yeah, this looks good. Then they define sum dash of dash square squares xy x plus square x and square y. Close that one and close that one. Then we can do sum dash of dash square sum of squares 3, 4. Uh-oh, what did I do? I left out the plural sum of squares. 25. What if I do 3, 4, and 5? Invalid number, scheme error, invalid number of arguments. Current eval stack 0, sum of squares 3, 4, 5. Okay. This is making sense. And then we could do define f of a as sum of squares plus a1 times a2, and paren a bunch of times. That should come out as 136. Oh, I have to actually run f of 5. Sum of squares. Okay. That's better. Okay, 1.1.5. The substitution model for procedure application. To evaluate a combination whose operator names a compound procedure, the interpreter follows the same process as for combinations whose operands name primitive procedures, which are described in section 1.1.3. That is, the interpreter evaluates the elements of the combination and applies the procedure, which is the value of the operator of the combination, to the arguments, which are the values of the operands of the combination. We can assume that the mechanism for applying primitive procedures to arguments is built into the interpreter. For compound procedures, the application process is as follows. To apply a compound procedure to arguments, evaluate the body of the procedure with each formal parameter replaced by its corresponding argument. To illustrate this process, let's evaluate the combination F5. Oh, they're going to go further into detail of this example. That's nice. Where F is the procedure defined in section 1.1.4. We begin by retrieving the body of F, square of sums plus A1 plus A2. Then we replace the former parameter A by the argument 5, sum of squares plus 5, 1 times 5, 2. Thus, the problem reduces to the evaluation of a combination with two operands, 1, 2, and an operator sum of squares. Evaluating this combination involves three subproblems. We must evaluate the operator to get the procedure to be applied, and we must evaluate the operands to get the arguments. Now, plus 5, 1 produces 6, and times 5, 2 produces 10, so we must apply the sum of squares procedure to 6 and 10. These values are substituted for the formal parameters x and y in the body of sum of squares, thus reducing the expression to plus square 6, square 10. If we use the definition of square, this refers to plus times 6, 6, and times 10, 10, which reduces by multiplication to plus 36, 100, and finally to 136, like we saw over here. Okay, this is good. The process we have just described is called the substitution model for procedure application. It can be taken as a model that determines the meaning of procedure application insofar as the procedures in this chapter are concerned. However, there are 2 points that should be stressed. The purpose of the substitution is to help us think about procedure application, not to provide a description of how the interpreter really works. Typical interpreters do not evaluate procedure applications by manipulating the text of a procedure to substitute values for the formal parameters. In practice, the substitution is accomplished by using a local environment for the formal parameters. We will discuss this more fully in chapters 3 and 4 when we examine the implementation of an interpreter in detail. Over the course of this book, we will present a sequence of increasingly elaborate models of how interpreters work, culminating with the complete implementation of an interpreter and compiler in chapter 5. The substitution model is only the first of these models, a way to get started thinking formally about the evaluation process. In general, when modeling phenomena in science and engineering, we begin with simplified incomplete models. As we examine things in greater detail, these simple models become inadequate and must be replaced by more refined models. The substitution model is no exception. In particular, when we address Chapter 3, the use of procedures with mutable data, we will see that the substitution model breaks down and must be replaced by a more complicated model of procedure application. Applicative order versus normal order. According to the description of evaluation given in section 1.1.3, the interpreter first evaluates the operator and operands, then applies the resulting procedure to the resulting arguments. This is not the only way to perform evaluation. An alternative evaluation model would not evaluate the operands until their values were needed. Instead, it would first substitute operand expressions for parameters until it obtained an expression involving only primitive operators, and would then perform the evaluation. If we use this model, the evaluation of f of 5 would proceed according to the sequence of expressions. Sum of squares plus 1, 5 times 5, 2 plus square plus 1, 5 square times 5, 2 plus times plus 5, 1 plus 5, 1 times 5, 2 times 5, 2 followed by reductions plus of times 6, 6 and times 10, 10 plus of 36 and 100 given 136. This gives the same answer as our previous evaluation model, but the process is different. In particular, the evaluations of plus 5, 1 and times 5, 2 are each performed twice here, corresponding to the reduction of the expression times xx, with x replaced respectively by plus 5, 1 and times 5, 2. This alternative, fully expand and then reduce, evaluation method is known as normal order evaluation, in contrast to the evaluate the arguments and then apply method that the interpreter actually uses, which is called applicative order evaluation. It can be shown that for procedure applications that can be modeled using substitution, including all the procedures in the first 2 chapters of this book, and that yield legitimate values, normal order and applicative order evaluation produce the same value. See exercise 1.5 for an instance of an illegitimate value where normal order and applicative order evaluation do not give the same result. Lisp uses applicative order evaluation partly because of the additional efficiency obtained from avoiding multiple evaluations of expressions such as those illustrated with plus 5, 1 and times 5, 2 above, And more significantly, because normal order evaluation becomes much more complicated to deal with when we leave the realm of procedures that can be modeled by substitution. On the other hand, normal order evaluation can be an extremely valuable tool, and we will investigate some of its implications in chapters 3 and 4. Okay, I want to back up and try to understand this a little better. F of 5. So this is normal order, where we apply sum of squares, or is this applicative order? I think I might just leave a note to come back to this. Okay, structure and notes. We can close Untitled, delete. Normal order versus applicative. Order evaluation. That's going to be worth some review, but I'm going to press on for now. (1.1.6) Conditional expressions and predicates. The expressive power of the class of procedures that we can define at this point is very limited because we have no way to make tests and to perform different operations depending on the result of a test. Okay, here we come conditionals. For instance, we cannot define a procedure that computes the absolute value of a number by testing whether the number is positive, negative, or 0 and taking different actions in the different cases according to the rule absolute value equals x if x greater than 0, 0 if x equals 0, minus x if x less than 0. This construct is called a case analysis, and there is a special form in Lisp for notating such a case analysis. It is called cond, which stands for conditional, and it is used as follows. Okay, let's type this one out. Define abs of x is conditional of greater x0 x oh, I left out a paren there. Greater x0 x equal x0 0 less than x0 minus x, close, 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 close. Then abs of minus 5. Should give me 5. Hey, I like this. The general form of a conditional expression is cond p1 e1 p2 e2 pn en, consisting of the symbol cond followed by parenthesized pairs of expressions p and e called clauses. The first expression in each pair is a predicate, that is, an expression whose value is interpreted as either true or false. Conditional expressions are evaluated as follows. The predicate p1 is evaluated first. If its value is false, then p2 is evaluated. If p2's value is also false, then p3 is evaluated. This process continues until a predicate is found whose value is true, in which case the interpreter returns the value of the corresponding consequent expression, e, of the clause as the value of the conditional expression. If none of the p's is found to be true, the value of the cond is undefined. Ooh. The word predicate is used for procedures that return true or false, as well as for expressions that evaluate to true or false. The absolute value procedure abs makes use of the primitive predicates greater than, less than, and equal. These take two numbers as arguments and test whether the first number is respectively greater than, less than, or equal to the second number, returning true or false accordingly. Another way to write the absolute value procedure is define abs x conditional of greater than x0 minus x else x, which could be expressed in English as if x is less than 0, return minus x, otherwise return x. Else is a special symbol that can be used in the place of the p in the final clause of a cond. This causes the cond to return as its value the value of the corresponding e, whenever all previous clauses have been bypassed. In fact, any expression that always evaluates to a true value could be used as the p here. Here is yet another way to write the absolute value procedure. Define abs x if less than x0 minus x, x. This uses the special form if, a restricted type of conditional that can be used when there are precisely two cases in the case analysis. The general form of an if expression is if predicate consequent alternative. To evaluate an if expression, the interpreter starts by evaluating the predicate part of the expression. If the predicate evaluates to a true value, the interpreter then evaluates the consequent and returns its value. Otherwise, it evaluates the alternative and returns its value. In addition to primitive predicates such as less than, equal, and greater, there are logical composition operators which enable us to construct compound predicates. The three most frequently used are these: and, expression 1, ... expression end. The interpreter evaluates the expressions e, one at a time, in left to right order. If any e evaluates to false, the value of the and expression is false, and the rest of the e's are not evaluated. If all e's evaluate to true values, the value of the and expression is the value of the last one. Which is true, right? Do I have that right? Or of e1 ... en, the interpreter evaluates the expressions e one at a time in left to right order. If any e evaluates to a true value, that value is returned as the value of the or expression, and the rest of the e's are not evaluated. If all e's evaluate to false, the value of the or expression is false. What if this last one wasn't a Boolean? Like, okay, and true, bananas. Unknown identifier bananas. What about 5? Weird. I feel like I shouldn't be able to put a 5 there, right? But I can, so. What about, hold on. How about and true 4, 5? Oh. What about and true 0, 7? Is 0 truthy? What about undefined? Unknown identifier undefined. Well, yeah, that doesn't. What if I do a cond with five equal 5, 6, 5, 8, and this cond is gonna come out to undefined. But undefined is still not false, so the and gives me 9. That's weird. Let me just see this cond equal 5, 8. Wait a second. You're telling me cond of equal 5 and 8 gives me 8? What about econ of equal? Wait a second. I think I need to back up. I think I'm making all kinds of logic mistakes. Let's work with cond a bit. Cond of equal 5, 8. Six. Let's back up. So what was I doing here? And why on earth was that giving me 5? Maybe it's not very meaningful to put a, or like I need to do a, put that there, unexpected token. Equal 8, 5. This should give false. Okay. Cond equal 8, 5. 5. 6. 4. Yeah, I don't understand that at all. Anyone in chat have any idea what's happening there? Oh, but in any case, it's a rest time. Okay, that's it for that break timer. So we're back in with 1.1.6 conditionals. And I was getting a little bit, or maybe I got through that. Okay, I was playing with examples and I got confused by this thing, which I'm just gonna let it stand that was a weird thing to try and not worry about the reason why it came out to what it came out to. Okay, not E. The value of a not expression is true when the expression E evaluates to false and false otherwise. Notice that and or are special forms, not procedures, because the sub-expressions are not necessarily all evaluated. Not is an ordinary procedure. As an example of how these will be used, the condition that a number x be in the range 5 less than x less than 10 may be expressed as and greater than x5 less than x10. As another example, we can define a predicate to test whether one number is greater than or equal to another as define greater than or equal to xy as or greater than xy equal xy. Or alternatively as define greater than equal to xy not less than xy. Okay, exercise 1.1. We're into the exercises. Woohoo! Below is a sequence of expressions. What is the result printed by the interpreter in response to each expression? Assume that the sequence is to be evaluated in the order in which it is presented. Okay, I guess I'll be working through these. 10, I'm going to say is just 10. Let's check it. Yeah, it's 10. Can I copy paste from one place to the other here? Plus 5 and 3 and 4. Basic math, what is that, 12? Yeah. Minus 9, 1, that's going to be 8. Divide 6, 2 is going to be 3. What about divide 7, 2? Oh, it has floats. Oh, that's interesting. What do I do double divide? Is that integer divide? Unknown identifier. Although I can define slash, oh, but I have no idea how to round down. I don't feel like doing that right now. Okay. Plus times 2, 4. That's going to be like plus of 8 and minus 4, 6. 4 minus 6 would be minus 2. So the result is going to be 6. Minus 2. Cannot call a 8. Okay, that's what the problem is. Define A3. That won't have any output, but it'll be useful for later. Define B plus 1A, and then plus AB times AB. Wait, what? Oh, we defined A as 3. That's like 3. And B we defined as plus A and 1, so 4. Times 3, 4. 3 times 4 is 12. Plus 4 is 16. Plus 3 is 19. So these two should give 19. Yeah, okay. Cool. Equal AB, that should give false. This one's kind of nasty. If and greater than B, A, that's true. Less than B, times AB. So times AB is 3 times 4 is 12, and B is less than that. So this whole and is true. The result is going to be B, so we'll get 4. Whoa, it just, I didn't even hit enter, it just went. Okay. Excuse me. Conditional. Equal A4, no, that's false, so we don't evaluate the 6. Equal B4, that's true, so we do evaluate the plus 6, 7A. And A was 3, so the 16 is the result. And I keep forgetting that if I click my mouse outside of this editor, then it evaluates the result. Okay. Plus 2, if greater than BA, B else A. So it's at plus 2 and 4 is 6. Yes. Then times cond greater than AB, no. Less than AB, yes. B is 4. So times 4 and A plus 1 is 4. 4 by 4 is 16. Okay. Ooh, this looks nasty. Translate the following expression into prefix form. Okay, well, start with, wait, what is this? This is I think that's 5 plus 4 plus whatever. So plus 5 for all this stuff minus 2 all this stuff minus 3 all this stuff minus plus 6 divide by 1, 3, and we have to divide all of that by all of that, and we have to take multiply 3 by result and the result, and that's minus 6 and 2, and that's minus 7 and 2. So 1/3 plus and 6, 1/3 minus, I think that's extra. So divide all the top stuff by all the bottom stuff. And on the top we have 5 plus 4 plus the result of all this. And the all this, oh, well, I got a number, but it doesn't help or hurt because I don't know what it was supposed to come out to, so. Actually, I guess I could just do that on my pocket calculator or like on an internet calculator. Let's see if I got it right. 5 plus 4 plus 2 minus 3 minus 6 plus 1 divide 3, close, 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 close. Is that too many? That's the right amount. Divided by 3 times 6 minus 2 times 2 minus 7 equals. Oh, no way. I can't just type that into Google and get the answer? Ah, where'd it go? Calculate that. Okay, fine. Correct. Calculate fractions calculator. Oh no, I lost it. You know what? I understand the idea of this. I'm satisfied of that, so let's move on. Okay, exercise 1.3. Define a procedure that takes 3 numbers as arguments and returns the sum of the squares of the 2 larger numbers. Ooh. Well, for starters, we can reuse some code from above. There's sum of squares. And there's define square. But the tricky part is we have 3 numbers. We have 3 numbers and we have to return the largest 2 of them. Well, let's define largest 2, paren largest 2 of A, B, C. The trick can be to, we can say if and less than A, B, and less than A, C, then A is the smallest. So cond we have the and. If that's all true, then we return can I return 2 things? Is that legal? Anyway, and less than BA less than BC. Then B is the smallest, so we do A and C. Else, right? BC. Now give me largest 2 of 3, 4, and 5. Ah, no, it's only giving me the 4. What if I do 3, 5, and 4? This is tricky. So really what I have to do is I have to find I have to define largest of ABC and also define middleist of A, B, and C. How about we just call it middle? So if greater than A and B, I didn't mean to click outside of there, I'm sorry, computer. And greater than AC, then we return A. Otherwise, if greater than, let's delete this line. How do I comment things? Is that a comment? Is that a comment? I don't know what a comment is. Define middle ABC. For now, we'll just do A as like a stub. If B is greater than A and B is greater than C, then we return B, else we return C. Okay, let's try that out in all of the, 3, and then 5, 4, 3. Still gives me 5. Okay. Define middle of ABC. Let's do a cond expression. With and if A is in the middle, then we can have it satisfy C less than CA and greater than BA. CTY, hello. CTY says, what is this? This is... Let me show you what this is. This is Structure and Interpretation of Computer Programs from MIT Press by Harold Abelson, Gerard J. Sussman, and with Julie Sussman. And I'm currently in Chapter 1 on Exercise 1.3. Define a procedure that takes 3 numbers as arguments and returns the sum of the squares of the 2 larger numbers. So I've got largest taken care of. Now I want to take care of middle. And I have these 3 numbers. And if it's the case that C is less than A and B is greater than A, then we can return A. If it's the case that and, we just need to switch these around. If C is the one in the middle, greater than... Of course, this is tricky because we might need to worry about like if they're the same, but I'm not going to worry about that for now. A and C, if greater than A, B, let's do this for B. So if A is less than B and C, wait a second. Well, what if it's we have to, like, there are multiple possibilities, right? Because just because A is in the middle, A could be the large, like if A is in the middle, it could be that C is the smallest and B is the biggest, or it could be the other way around. So I actually need an OR here. Okay, this is bad. Lisp calculate second largest number. Well, I haven't learned how to sort yet, so that's not very helpful. I might be stuck on this problem. One way to kind of hack it out is how much time we got left? I'm gonna focus in on this MIT stuff for at least the rest of this timer, although I may skip exercise 1.3 for now. What am I hearing? Whatever it is, it's gone now. Hey, Sammy, are you gonna come over here? Are you gonna walk in front of the camera? Come on, Sammy. Oh, there he goes. He's the big black blob, the big gray blob in front of the camera. Hello, Sammy. How are you tonight? I can't see, but I'm petting you. Okay, Sammy, move along. Move along. I've got a stream to do. Move along. Okay, good kitty. Okay, exercise 1.4. Observe that our model of evaluation allows for combinations whose operators are composed expressions. Use this observation to describe the behavior of the following procedure. What? Define A plus abs B, A, B, if greater than B and 0, plus, minus, say what? A, B. For starters, is that even valid code? Oh, well, I guess so. Let's do A plus abs B of 3 and 5. 8, okay. Oh, I get it. Oh, that is so clever. Chat, do you get it? It determines if B is greater than or equal to 0, and depending on that, it either gives you plus or minus. And then that all resolves to plus or minus, and so we're either taking A plus B or taking A minus B. Huh. That's really darned clever. Okay. Exercise 1.5. Ben Bit-Diddle has invented a test to determine whether the interpreter he is facing is using an applicative order evaluation or normal order evaluation. He defines the following two procedures. Define P. What? Define test xy. If equal to x0, 0 else y, then he evaluates the expression test 0p. What behavior will Ben observe with an interpreter that uses an applicative order evaluation? What behavior will he observe with an interpreter that uses normal order evaluation? Explain your answer. Assume that the evaluation rule for the special if form is the same whether the interpreter is using normal or applicative order. The predicate expression is evaluated first, and the result determines whether to evaluate the consequent or the alternative expression. We're almost running down on the timer here. So I don't know if I want to get started on square roots by Newton's method. Okay. Let's get started at looking at 1.1.7 example square roots by Newton's method, and then decide what to get into in the next section of the stream. Procedures, as introduced above, are much like ordinary mathematical functions. They specify a value that is determined by one or more parameters, but there is an important difference between mathematical functions and computer procedures. Procedures must be effective. As a case in point, consider the problem of computing square roots. We can define the square root function as square root x equal the y such that y greater than equal to 0 and y squared equal x. This describes a perfectly legitimate mathematical function. We could use it to recognize whether one number is a square root or another, or to derive facts about square roots in general. On the other hand, this definition does not describe a procedure. Indeed, it tells us almost nothing about how to actually find the square root of a given number. It will not help matters to rephrase this definition in pseudo-Lisp. Maybe I will be wanting this matter. Define sqrtx, the y, and y greater than or equals 0 equals square yx. This only begs the question. Well, first off, what happens if I try to run this thing? Sqrt of 5. The is undefined. Okay. Fair enough. The contrast between functions and procedures is a reflection of the general distinction between describing properties of things and describing how to do things, or as it's sometimes referred to, the distinction between declarative knowledge and imperative knowledge. In mathematics, we are usually concerned with declarative what is descriptions, whereas in computer science, we are usually concerned with imperative how-to descriptions. How does one compute square roots? The most common way is to use Newton's method of successive approximation, which says that whenever we have a guess y for the value of the square root of a number x, we can perform a simple manipulation to get a better guess, one closer to the actual square root, by averaging y with x divided by y. For example, we can compute the square root of 2 as follows. Suppose our initial guess is 1, guess quotient 2 divided by 1 equal 2, average 2 plus 1 divided 2 is 1.5. When we have 1.5, 2 divided by 1.5 is 1.3333. Take the average, we get 1.4. 1.4 divide and get 1.418. Take the average and get 1.4142. And 1.4142 ... and so on. Continuing this process, we obtain better and better approximations to the square root. Now let's formalize the process in terms of procedures. We start with a value for the radicand, the number whose square root we are trying to compute, and a value for the guess. If the guess is good enough for our purposes, we are done. If not, we must repeat the process with an improved guess. We write this basic strategy with a procedure. Define square iter guess x, if good enough question mark guess x, guess, else square iter improve guess x of x. Let me write all that down and see if I understand it. Define sqrt-iter guess x, if good enough question mark guess x, then the answer is guess. Otherwise, we do the sqrt iter, so it's a recursive call. Improve guess x. Wait, I'm lost in this last bit. What's happening here? Square iter of x is the radicand. Improve guess with respect to x, and to the square iter of this result with x. This book is getting deep pretty quick. A guess is improved by averaging it with the quotient of the radicand and the old guess. So define improve guess x, average guess, divide x guess, 1, 2, 3, where define average xy is divide plus xy to end. We also have to say what we mean by good enough. The following will do for illustration, but it's not really a good test. See exercise 1.7. The idea is to improve the answer. That's the end of this timer, but let's go on a little bit further. The idea is to improve the answer until it's close enough so that its square differs from the radicand, by less than a predetermined tolerance here, 0.001. Define good enough, question mark, guess x less than abs minus square guess. So we're going to need to pull back our definitions for square and abs, x, and 0.001, close. Finally, we need a way to get started. For instance, we can always guess the square root of any number is 1. Define sqrt, find sqrtx, sqrt iterative 1.0x, go. If we type these definitions to the interpreter, we can use square root just as we can use any procedure. Square root 9, 3 point, blah, blah, blah. But before I do that, I have to define square as square of x as multiply x by x. And I have to define abs of x as if less than x0, then minus x, else x, close. Okay, this should give me a, oh yeah, I have to actually ask for something square root of 9. Let's do it. Goody nug, question mark. I just typed it wrong. Cannot call 16. Where did I make that mistake? Current eval stack 0 abs minus square guess. I don't know. I'm all brained out for the moment. Time to put on the BRB screen and a break timer. CTY, let me know if you're still here, because I might think about switching over to that JetBrains project if you're around. Let me know in the chat. All right. We are back. Welcome, chat. I know there's only apparently one viewer here, but I'm still gonna take a moment and say hello to you. What would the chat like to see now? You one person in the chat. I know I'm kind of putting you on the spot here, but I think we've done enough of the structure and interpretation of computer programs for tonight. I'm gonna put that in the bookmarks bar here to leave off where I am. What do we want? Do we want some coding game? Do we want some open source stuff? Coding game is nice because I get more viewers that way because the coding game website brings them into me. Just for instance, if I go to Clash of Code right now, how many people are currently live? No one. I'd be the only one. Yeah, I'm not hearing anything from CTY. They may not be hanging around right now. So let's do some coding game. What's all this? Okay, I just need to edit stream info. You know what? I should update it on YouTube too. What's all this 15 stuff? People followed me, clashes are over. Neat. I should move my T over here so I'm not hitting my mic stand with it every time. Alright, go back to this other scene. I actually put my tea over here, so you know when I'm taking a drink of tea. Gonna wait a little bit, see if some people trickle in. Also gonna see if I appear on their live notifier. It said it may take a few minutes depending on the API, so that's okay. There we go, I'm appearing now up there. Alright, let's try to clash. Fast as possible. Mirrored time number is a number of 2 digits x and y, which if we write xy colon xy or xy colon yx, we get a valid time in HHMM. Your task is to print the valid combination separated by spaces. If no such combination exists, print none. The results must be unique. Example, n equals 12, 1, 2, 1, 2, and 1, 2, 21. Okay. A comma B equals n dot split on the empty string possibilities, I cannot type for the life of me. Possibilities equals, we could have an F string with A, B, then colon, then A, B, and I want this to be a list of strings. There's probably a better way of doing this, like I could do inner tools or something, but I think the possibilities are A, B, B, A, then B, A, A, B, and B, A, B, A. For candidate and possibilities, if is valid of candidate, valid, let's call it valid, valid ones equal empty list. If is valid of candidate, valid ones dot append candidate, def is valid of C for candidate. Now let's import date time dot time from date time import time try t equals time C except return false, return true. Let's try this. Oh wait, value, wait, I can't split on the empty string? Okay, fine, equals n0 comma n1. And I have to remember to, where did I put valid ones? Oh, they're got stuck up there. Print space dot join valid ones. Try that. Didn't get any valid ones. Let's do a sanity check and see that C is actually getting printed out here. Oh, but I have to make them be not distinct. I mean, they have to be distinct. Okay, find.sparse. Okay, fine, I'll do it a different way. A comma B equals C dot split on the quote character if A less than equal to 12 and B less than equal to 59, return true, otherwise it's going to return false. String and int. Okay. Say int of A and int of B. Okay. Just throw a set in there and that should do it. Are you kidding me? They have to be in order? Did I read the question totally wrong? Oh, only the first of my things here are actually valid. Except this has to allow it to go up to 23. BA, not B1. Twenty-one 12, 21 21. Do I have to sort it in reverse? What if I take away the sorted now? Well, this is frustrating. I don't understand, like, what determines what order I'm supposed to return them. Also, I haven't handled the none case, but we'll get there. The order is the order of time. Thank you, Money Guess. That sounds helpful. Oh, okay. So I can do sorted this p equals lambda p equals f equal lambda val colon val 1 comma val 0. Let's try that. Money guess, if the order is time, then we got 2112, 2121. The ones that I'm getting wrong, unless it has to be reversed by time. See, this one, 1221. Okay, actually I got them all right now. I just have to deal with if length of valid ones equals 0, print none. Is it all caps none? Else print this stuff. Play all test cases. Oh no, I got one wrong. See, 2121 comes before 2112. None is fine. 0101 is fine. 1717 is fine. But 2 is bad. 2 is okay. But 3 is bad. Maybe is the order of the input then? Yeah, well, that's what I would have thought too, but if we take away sorted, well, wait, now even 1111 is wrong? Oh, because I printed two things. I get more of them right if I use my sorting here, so I think that's the one I'm going to submit in 37 seconds from now. Wait, they're all right now? No, number 2 is wrong. Now it's right. I don't understand. I'm just going to submit. It's a weird one, right, Money Gas? I don't get it. Actually, let's see if anyone has something. F5. What about F5? Clash is now complete. Let's play again. Funny guy says, don't understand, people don't share code. Oh, you're saying you don't understand and people don't share code? Yeah, I don't get that either. Especially if you got it right. Reverse mode, clash now. Oh, this looks cool. 4 by 4, right? 12 by... And they even give us some hints here with width and height. Row or top, and that's gonna be the same as the bottom, equals star times, and row equals star plus space times width minus 2 times width minus 2 plus star, and print top for for underscore in range height minus 2, print row, print paren row, print top. Let's try it. Play all test cases. Uh-oh. What's wrong with this last one? Oh, we have to deal with special cases. If height greater than 1, then we print it again. Try this guy. Play all test cases. Still a failure. Oh yes, okay. We'll equal that if width greater than 1, else just star. Okay, now we got this. Share my code. Let's see what Mao Ao has to say. If we got W and H. If W equal 1 for I in range H minus 2, print star. Else for I in range, okay, print I in range H minus 2, print such and such. If H greater than 1, print star times width. Yeah, same idea. Straightforward, says Money Gas. Yes, I agree. I got briefly hung up by some of the edge cases, but altogether straightforward. I'll hang out till 10 minutes and then move on to the next one. Like I said, I'll hang out until 10 minutes and then we'll go on to the next. Okay. Play again. Reverse mode, clash now. Looks like we're going from color rate. Looks like we're just converting color equal input A, comma B, comma C equals color 0 to 2, color 2 to 4, comma color 4 to 6. Money guess says input paren 1 colon. Oh yeah, good call, because we don't want the hashtag. Thank you, Money Gas. That was helpful. For who in A, comma B, comma C. I probably didn't need to even say colors. For C in colors, print C dot. Shoot, I don't know the function here. This is a Python, so we print decimal. Can I just do decimal of C comma base 16? Hex I can do, but that's going the opposite direction of where I want to go. I need like inverse hex. Alright, fine. I don't want to look this up though. Alright, fine. Def hex to decimal. Sixteens equals H for hex is H0 and ones equal H1. D equals, I can't believe I'm doing it this way, but okay. 0 goes to 0, 1 goes to 1, 2 goes to 2, 3 goes to 3, 4 goes to 4, 5 goes to 5, 6 goes to 6, 7 goes to 7. Maybe int ff of 16 goes to 255. Let's try that. Although now that I've started my own hexadecimal, I kind of want to Got him. Alright, I'm just gonna go for it. Let's see what we got. Interesting. Base convert function in PHP. Hey TV Josh, thanks for stopping by and thanks for the follow. No, I saw you earlier tonight. It's nice to see you again. Let's do one more and then I'll call a stream break. What's the assignment? Well, this is the game mode is reverse. So we just have to 13579. Is it just print out all the odd integers on a new line? I think that's all it is. For I in range of 1, comma, and we just do n by 2, print I. Don't need to print answer. Oh, we need n plus 1 so that it's inclusive. Boom. That was an easy one. I guess I can view code here. I'm pretty sure that's exactly the same code I used. Except I didn't do a plus in front of 2. Money Gas says boom. And I didn't comment, and I didn't delete this stuff, I just commented it. I feel like doing a golfing one, and for that I think I need to do a private clash. Shortest all languages, let's start. I'm going to close off this. We can share this in the Twitch chat if anyone wants to come along. But I'm only going to wait 1 minute this time, so when this hits 4, we're going. Thanks for dropping in, Mao. Mao. I don't know exactly how to say your name. All right, as promised, I'm going to go at 4. You will be given n binary numbers. Print the decimal sum of the odd numbers. I'm already thinking optimization on this because it's pretty straightforward. You don't need to maybe I do need to do I in range n. If input mod 2 equal 1, if I mod 2 equal 1 else 0. Oh, not I. Input. Oh, darn it, that's not going to work either. Alright, fine, we'll just do a list. Empty list. T dot append I print sum of, what was that ping for? Sum of x for x in T if x mod 2 equal 1. Oh, but these are binary integers. Let's see if I'm getting this close to right. Okay, so how can we shorten this as much as possible? Does it help me if I say I equal input? I think it does. Int object is not callable. Huh? What have I mixed up here? Well, whatever, that was a small fix. Oh. That's why. Anyone see a way to get this below 107? I'm not going to do the Unicode golfing trick. I'm not going to accept that level of unreadability in code for this challenge. Even if it could knock my number of characters down by a little bit. I like this song. I don't think there's any way to get around p.append, because I have to evaluate the input statement whether or not it's ultimately going to get added to the sum. What if I take away the 2 here? Does that make it fail? It does make it fail. Yeah, that's what I thought. Remove spaces. Right, there are a bunch of spaces here that I don't need. Should have thought of that one myself. Thank you, Money Gas. Well, that helps a little. Anything else obvious that I'm missing? I removed all the spaces that I could. The rest of them have meaning. Like, I can't take out that one. Oh, interesting. This checker doesn't realize that I changed my code back to the same stuff. It just knows that maybe it goes by the timestamp of when I last made a change. Now, what was that ping? I keep getting pings. I'll play all the test cases. Mao Ao over here is still hasn't submitted, but I think I'm going to submit. Give maybe a minute, see if this person comes in with a shorter answer. "65 characters. Now let's see, did they use the Unicode trick? Oh wow. I equals input. That's good, so you use that here and here. R equals 0, so we've got a sum going. Oh cool, you can fold in the for loop. So wait, how did I do that? Oh, so they broke it down into 2 lines. One to take S as the int of the input. Interestingly, like from an efficiency standpoint, we're doing the integer calculation even if I is not going to end up getting used, although you have to do the integer calculation to determine whether I was going to get used. Money Gas points out you can replace print by input. That's true. I forgot about that detail as well. So I could have done I here. And this, I like this dot times. It's just a little bit less than the range and parenthesis. It's pretty good. Okay, I'm going to call a stream break. Stay tuned to find out whether I'm going to keep streaming anymore tonight after this break. I would tell you, but I don't actually know myself. Okay, that does it for the stream break. And if anyone was taking bets, I doubt that, but just in case, that does it for the stream as well. I'm gonna call it for tonight, feeling like I'm at the end of my streaming journey for tonight. Oh, and Money Gas says GG on that last coding game, so thank you. Thanks for stopping by. Thank you, TV Josh, again for that follow a little earlier. And CTY we haven't heard from for a while, but thank you, CTY, for stopping by tonight as well. And yeah, everyone, if I don't see you, have a good night. I mean, I won't see you tonight. What am I talking about? Unless I decide to stream again in like 30 minutes, but I don't think I'll do that. What am I saying? Okay, let's find someone to raid. Oh, 2 viewers, is it even worth it? Yeah, it's worth it. I should have raided someone this afternoon, but I didn't think about it, so let's just form those good habits and go raid someone now. Here we go. This looks like one we can raid. Waiting for the ad. Waiting for the ad to finish so that I'll actually see it. Okay, here we go. All right, thank you, loyal 2 viewers. I hope I reward you with a good channel to go to. And it's going to take a moment to actually make the raid happen, but we're going to do it. Okay. Have a good night.